In this section, we're going to evaluate first-order differential equations and look at general solutions and particular solutions. A general solution to a differential equation is a solution that has basically a constant of integration here. So when it has a constant of integration where we haven't really figured out a particular value, we just use a constant, and we don't know what that particular value is, then it just represents kind of a family of functions that behave as, in this case, behave as e to the power negative 2x. And so this is a general solution of this differential equation. And that's a differential equation because there is a differential expression as part of that equation. So that's how we give it the name a differential equation. Looking down at this next equation here, this is a second-order differential equation. If you notice, it's got two constants of integration. A little more complicated, but basically it's integrating this expression twice and putting in constants of integration each time we integrate to get this basic expression. So here we're integrating once, and here we're integrating twice. So two integrations get us a second-order differential equation. A single integration gets us a first-order differential equation. So if we want to verify if something's a solution to a differential equation, we need a differential expression, and we need to have something to plug into that differential expression. So this is the expression for y. We need to come up with an expression for y prime. So go ahead and take the derivative of here, which is minus e to the minus x. So now we have expressions for the two, the differential expression and the variable expression y, and we can just plug those in. So we have 3 times the quantity minus e to the minus x plus 4 times the quantity e to the minus x. And basically what we're doing is we're checking whether or not that is mathematically equal to e to the minus x. So do a little distribution here, and it only takes a step or two to come to the conclusion that, in fact, when we do the math here, we get e to the minus x, which is definitely equal to the right-hand side. So in this case, the answer is yes, that this is a solution to the differential equation. Again, another example that's really similar to it is verifying that this is a solution to this differential expression. So we have the expression for y. We need a expression for the derivative of y. So taking the derivative of this, we're going to have to go ahead and use that power rule here. So if we kind of do a u sub here, we can take the derivative of negative cosine x, that's sine x, times e to the minus cosine x. And if we plug that into this differential expression, then we have sine x times e to the minus cosine x equals e to the minus cosine x times sine of x. And so we're questioning as to whether or not those are mathematically equal to each other. And we could rearrange this just to make the point, I guess. And we can see that those are, in fact, equal to each other. So again, yes. E to the minus cosine x is a particular solution to this differential equation. Complicated example, we want to verify that this is a solution to this first-order differential equation. So taking the derivative of this is slightly more complicated. We have to use the product rule. So we'll take the derivative of the first, which is 2x, times the second, plus the first times the derivative of the second. So there's the expression for the derivative, and when we plug that into here, we're going to have x times the derivative, which is 2x e to the x, plus x squared e to the x, minus 2 times the expression for y, which is x squared times e to the x, and we want to know if that is equal to x cubed e to the x. And so simplifying here, we can distribute the x into the brackets. And distribute the 2. And we can see that those expressions cancel, so we're left with x cubed e to the x, and that in fact is equal to the right-hand side of the equation. So again, yes, this is a solution to the first-order differential equation. The two terms we really have to be able to differentiate between are the terms particular and general. Okay, the particular solution is when we actually find a numeric value for these constants of integrations. Right now, this paragraph is basically telling you that this is a general solution because there's a constant of integration here. But if we have a set of initial conditions, like we have down here, then we can put in those initial conditions to the differential expression and the solution to that differential expression, and come up with a particular solution that no longer has these constants of integration. From a graphical standpoint, we look over here and we can see that this general solution of a constant over x gives us this family of solutions that are asymptotic with the x and the y axes. And so as we integrate this and set up the constants of integration, we can then come into this particular solution. Of course, if the constant of integration is 1, we get this curve like this, and as we increase that constant of integration, we get these curves that are farther and farther away from the origin. So to set up that particular solution, we'll use this example of here's an equation, a general solution, and here's a differential expression. And it says we're going to verify that the general solution satisfies a differential equation, and then find the particular solution that satisfies the initial conditions. And these are the initial conditions right here. So if we take a look at the general solution here, that's this. That general solution has that constant of integration. And we take the derivative with respect to x of that general solution. Taking the derivative of 3x squared gets us 6x. Taking the derivative with respect to x of this portion of the general solution, you're going to have to use the chain rule. So we're going to have to take the derivative of y and then use the chain rule with dy dx. So taking the derivative of this would be 4y, and then dy dx equals 0. And then if we then solve for the differential expression dy dx, taking the 6x over to the other side, we have 4y dy dx equals negative 6x. And divide each side by 4, we have dy dx equals negative 6x over 4y, and we can reduce that to negative 3x over 2y. And so we have an expression then for the differential expression, and we can plug that into this differential equation. And when we do that, we get 3x plus 2y y times the quantity, here's the differential expression, minus 3x over 2y. And we're going to check, we don't know, but we want to check that this mathematically is equal to the right-hand side, which is 0. So if we simplify this, we get some canceling occurring here, and so the question is does that equal 0? And when we evaluate that, in fact, yes, it does equal 0. So we've confirmed that the general solution is does satisfy the particular solution. Does satisfy the differential equation. Excuse me, I said that wrong. So if we want to find the particular solution for this, we can then use these values as initial conditions. So, for instance, what is our constant of integration? So we're going to have to find C. That's what really we're talking about when we're talking about finding the particular solution. So we have these initial conditions here when y equals 3, x equals 1. So we're going to go ahead and substitute that in. X is a value of 1. Y is a value of 3. And what does that get us for our constant of integration? And so when we evaluate this, we get 3 plus 18, and that is 21. So our constant of integration is 21. So our particular solution then looks like this. It looks like 3x squared plus 2y squared equals 21. So when we're looking at this, we're looking at something that is circular in shape. It's a conic section. In fact, it's an ellipse if you want to get really picky about it. We know that by our x squared and our y squared terms and the fact that there are two different coefficients in front of the x and the y. For this example, we're going to use the integration capabilities to come up with a general solution to this differential equation. And so if we separate the differentials, taking dx to the other side, we have dy equals x times cosine quantity x squared dx. And so integrating this looks like our best approach here would be a u sub. We could say u equals x squared and du equals 2x dx. And we have an x dx here, so we need a 1/2 du to substitute out the x dx. So substituting this out then gets us cosine of u, oops, cosine of u times 1/2 du. And setting this up for integration, then we can just throw an integral sign out front, and we are going to be integrating, I'm going to pull out the half, we're going to be integrating cosine u du. And when we integrate cosine, we get the sine of u plus a constant of integration, and substituting back in our value of value for u is sine x squared plus c. So there is the general solution for that differential expression.